we started to talk about these atoms that had incomplete valence shells that would want to form a chemical bond with another atom. Sorry, I'm just, oops. 1 second here. Sometimes it glitches and like somebody can join and they won't be muted, but now I think you're all muted. Ha, so you can't say anything. Ha. Just kidding. All right, let's begin by starting where we left off. Begin by where we finished. Last time we finished talking about ionic bonds. It was our first type of chemical bond that atoms will form when they have incomplete valence shells, those outermost shells that weren't completely full. And we learned, right, that the first shell contained a maximum of how many electrons? Maybe this is ringing some bells. 2, exactly. And then our second shell contained a maximum of how many? 8. And our third shell, 8 as well. I rhymed. All right, so oftentimes our atoms will not have a full outermost shell, and to be in its most stable form, which is what atoms want, it is a law of our universe, we want to be in the most stable energy state, we want those full shells. And to do so, we gotta bond with another atom. We gotta either share an outer electron with another atom, or we gotta accept an electron or transfer one. We're gonna explore this in depth. The first type of bond that can form is called an ionic bond. So get the slides up. 3 kinds that we'll be talking about. First, ionic bonds. And as we discussed on Thursday last week, we always start with neutral atoms, right? Neutral atoms, meaning that we have an equal number of protons as we do electrons in the atom. The number of protons equals the number of electrons. This is where we always start. We are working with neutral atoms. So the protons in the nucleus, if we're talking about, let's say, oxygen has 8 protons in its nucleus. That's an 8+ charge. If we are working with a neutral atom of oxygen, we have 8 electrons in its shells, which would give it an overall charge of 0. Okay, so we're going to play with this a little bit when we talk about ionic bonds. First thing that can happen is that this neutral atom can lose electrons, 1 or more electrons. So let's pretend this neutral atom loses electrons, or an electron, 1 or more. And when a neutral atom loses an electron, we call it a cation. It becomes a cation. A cation, let me start with this. If I'm losing electrons, E-, right? These are negatively charged subatomic particles. If I lose a negative charge, it might become more negative or am I becoming more positive? I'm losing a negative charge. I'm getting rid of something negative. Exactly, I'll have more positive. Exactly. So a cation is it's defined as a positively charged ion. Positively charged ion. So an ion, so I'll just put a plus here. An ion is an atom that either loses electrons, and then we're going to be talking about the opposite situation where a neutral atom will gain an electron. And so an ion is an atom that will have an overall charge to it, either positive or, when we do the other situation, negative. So this cation is an ion. It's a type of ion. It's a positively charged ion. Now, a funny way to remember this, kind of just as things I've heard over the years of learning chemistry and biology. If you like cats, then cats are positive in your life. There you go. Or if you hate cats, you can just be like, well, I positively hate them. Another funny way to remember, not funny, but see how there's a T in cation here that's kind of like a plus sign? That helps. Anyway, all right, let's talk about the next situation that can arise here. When a neutral atom gains electrons, or an electron. So we are adding electrons, or one electron, to this neutral atom. We call this now, this neutral atom has now become an anion. An anion. If I add a negative charge, it's kind of crazy wording there, but if I gain, it's another word for gain or add. Can't think of any. But if I gain a negative charge, if I'm more negative, I'm more negative, right? So this is an anion is a negatively charged. We have added more electrons, which are negatively charged. Negatively charged ion. So this is a minus. Sorry, let me look at the chat here. Oh, is it choppy? Really? Oh boy. Am I running too many things right now? Let me try quitting some of my windows. Never know, that might help. Okay, just quit out of internet. Quit my okay, everything on my computer has quit. Let me eject this to my flash drive. You never know, that might have something to do with it. Take that out. Okay. Hopefully that helps. How's it doing now? Not too choppy. It's better? Oh, hey, there you go. Okay, I'll remember that. That's new. Cool. All right. Did you guys miss any of it? So, like, should I repeat any of this. Is anything unclear here? We're talking about neutral atoms. Oh, bummer. I can try doing a new, yeah, let's try doing a new Zoom. You never know, that might help. So you know what I'm gonna do, guys, is start a new Zoom session, and then email. It's not that bad? Okay. Can we power through it? Just ask me to repeat anything if it chops out or if you miss. You can still hear everything? Okay. Okay. Maybe everyone's like using Zoom right now. Oh well. Okay. Well, anyways, let's continue. So, I sound robotic. Oh boy. Okay. Well, just kind of victims of circumstance, aren't we? Sort of with Zoom and how we have to teach these days, but yeah, it's kind of annoying. I miss the classroom, man. Oh well, all right. So we've got a positively charged ion, got a cation that lost electrons. We've got a negatively charged ion, an anion, that has added electrons to it, or 1 electron to it. What's that saying about opposites that we've heard our whole lives? What do? They attract. Exactly. That's what happens. And they form, in this case, an ionic bond. Okay, questions about this? We're gonna do an example of an ionic bond now. Okay. So let's take a look at 2 ions that'll form an ionic bond. Okay. First one we're going to look at is a sodium atom with atomic number 11. So this sodium atom, we're going to draw the Bohr model for a sodium atom, kind of recalling from last lecture on how we do that. So sodium, I'm going to draw its nucleus first, and I'm going to put an Na inside. That's the chemical symbol for sodium. Has to do with its Greek root, Na. And so we know from the periodic table or in my slide that a sodium atom has 11 protons. That's what the atomic number is, right? So a sodium atom has 11 protons. Now, as we know, we are working with neutral atoms, so how many electrons does sodium have? 11, yes, let me add this person. Okay, yes, we have 11. 11 electrons. so that we get that overall zero, no charge, right? 11. Let's draw the Bohr model. So first shell, how many electrons? 2. 1, 2. Now we maxed out. Actually, I ran out of room, so I'm gonna. Okay. So we maxed out, so we're gonna go to the next shell. Okay. We used 2 electrons. How many do we have left? Not 8. We got 9. Yeah. I think I know what you're thinking. 8 is how many will fit in here. We've got 9 left. So let's start doing that. 1, 2, 3, 4, 5, 6, 7, 8. Maxed out, right? Move on to the third shell. How many left? Just 1, exactly. Boom. Okay. So that's what the Bohr model for sodium would look like. Let's move on to our another atom here. But first, I'll mention, is that a happy state? Is sodium content, stable, like this? No, we want full shells. So this third shell, he wants either 7 more, or maybe even lose that electron so his shells are full, right? His first 2 shells. But that third shell is looking unstable to me. Okay, let's just take a moment to look at another atom for a second here. Chlorine. Let's take a look at chlorine. Chlorine has atomic number 17. So let's draw chlorine. Chlorine in green. Chemical symbol in the nucleus here. So a chlorine atom has 17 protons. Working with neutral atoms, we have 17 electrons for no charge. 17 electrons. Okay, let's draw it. First shell, 1, 2. Second shell, how many do we got left? This is serving as a good review of last lecture. We have 17 to work with. Now we have 15 left exactly. So let's draw 1, 2, 3, 4, 5, 6, 7, 8. Still got more electrons. Move on to that third shell. How many left do we have? We've used 10 so far. We have 17. We got 7 left. 1, 2, 3, 4, 5, 6, 7. All right. So what do you think will happen here? Chlorine isn't happy and sodium's not happy. Chlorine has 7 valence electrons, the electrons in its outermost shell. The third shell holds a maximum 8. We want full shells. So chlorine wants 8 in its full shell, or in its third shell, right? So Anastasia, exactly. To satisfy both atoms here, the solution is that sodium is going to say, hey, you have an empty spot, and I have this awkward third shell with only 1 electron in it. I'm going to go ahead and give you it. I'm just going to transfer it over, just like that. I'm going to emphasize this again in a minute, but sodium is actually taking its electron. I'm just pretending it's this marker here. Taking its electron and giving it to chlorine entirely, as in transferring the electron. No sharing involved. You'll see why I'm emphasizing this when we talk about our next bond. but sodium is doing a complete transfer of this electron to chlorine. Okay. Now, once sodium does that, sodium no longer has a third shell, and its first and second shells are full. It's happy. All of its shells will be full. But if we take another look here, sodium still has 11 protons. It's still sodium, but it lost an electron, right? It completely transferred it to this chlorine. So it no longer has 11 electrons, it has 10, okay? So when we go from 11 protons, now we have 10 electrons. We gave one up to chlorine. We've got a 1+ charge left over. What do we call this atom now? What is this sodium atom now? Has a positive charge to it. Cation, totally. So we have a sodium cation here. Okay. Now let's take a look at chlorine. Chlorine gained an electron. Chlorine, we have given it an electron from sodium. So it now has, rewrite it up here in green. Still has 17 protons, right? Didn't change that. But now it has 18 electrons because it got one from sodium. So that's one electron left over, one minus charge, right? So we call this an anion. This is a chlorine anion. Now, because this sodium ion has a full plus charge and this chlorine has a full minus charge to it, these ions attract and they form an ionic bond between them. Positive and negative, they attract. And we're going to take a look at that on a slide and what this looks like, but we end up with NaCl. It's an ionic compound, and we're going to take a look at that really quick. But now, as you can see, sodium has all full shells. Chlorine, its first shell, second shell, and its third shell are now full. And this is what happens in nature in the formation of an ionic bond. And again, I'll mention one more time, I do this in class sometimes, that if this is sodium and this is chlorine, well, if this is a sodium's outer electron here, it's going to completely transfer it over. Take my electron, chlorine, here you go. Just give it to it. Again, it'll make sense why I emphasize that, because the next bond we talk about, that's not the case. There's no complete, here you go, take my electron transfer. Okay, questions about that? All right, let's take a look at the compound that this forms. So here is what we just drew out: sodium and chlorine. Sodium donating its electron entirely to chlorine. We get these two ions now: sodium cation, chloride, or chlorine. Chloride is the name for a negatively charged ion. So chloride anion, it's negatively charged. And this is what it looks like. These ions bind together, they attach to one another with this opposites attract kind of thing in forming, and these are all ionic bonds in between these ions. And NaCl is actually table salt, interestingly enough. So yeah, the salt you put on your steak and stuff, that's sodium chloride compound. Did I mention that's, that next? Where is it? Hold on. Oh, maybe it's in my notes. Hold on, let me check. Sorry. Sorry that made you dizzy. Okay, yes, I did. It's in my notes. So let's write it down. Na is sodium, yes. Yes, it's from the Greek thing. A Greek root for sodium, it started with Na. A lot of chemical symbols from the periodic table actually have weird abbreviations that don't make sense, like, what's another interesting one? Potassium is K. Like, how does that make sense, right? All has to do with the Greek root. Okay. So let me just write on the board here that NaCl, we call that, or any compound or substance that's composed of two or more atoms formed by ionic bonds, we call that an ionic compound. So NaCl is an ionic compound. And I totally misspelled. Ionic compound. Yes. So whenever you have two or more atoms that are bound together by an ionic bond interaction, we call it an ionic compound. So sodium chloride, or NaCl, is an ionic compound. Okay. Okay, the next thing I want to do is talk about our next bond. James Bond. Haha, just kidding. All right. Covalent bonds. That's our next bond, chemical bond that we're going to discuss. So I'm going to erase this. Okay. So I believe I have on my slide here. So let's talk about covalent bonds. Covalent bonds form when atoms share, colored, coded, and underlined, share one or more pairs of valence electrons. Okay. So I'll go ahead and write covalent bonds on the board first. Okay. Covalent. Oops. Covalent bonds. So if we go back to that definition of a covalent bond, atoms are sharing one or more pairs of valence electrons. So a pair of valence electrons, it's being shared. What we just saw was an entirely complete transfer. Here we are sharing. So to help sort of remember that, we can look at the word covalent. Co, that prefix there, means to share. So if you have a coworker, you're sharing work with your coworker. Co-pilot, you are sharing the pilot duty. Valent, of course, will refer to our valence electrons, our outermost electrons. And on our next slide, we're going to draw an example of probably the most important, famous example of a molecule that is formed by covalent bonds. And I use the word molecule because unlike ionic bonds or ionic compounds, where two or more atoms held together by ionic bonds forms an ionic compound, here two or more atoms that are held together by covalent bonds, we call it a molecule. All right, so what do I mean by sharing one or more pairs of valence electrons? Let's draw the water molecule, and then we'll be able to see what I mean by that. The water molecule. So if we take a, I'll keep the slide up here for a minute. First, water. Okay, water's molecular formula. What is water? What is water? Called it a molecular formula, kind of like NaCl was. H2O, yeah, nice. So H2O is what we're going to draw. And H2O means there's H2 is two hydrogens, right? Two hydrogen atoms, and then an O, an oxygen atom. So water is H2O, two hydrogens, one oxygen. Okay, so I have these up from the periodic table. If you recall, we can see the atomic number for both of these elements in the top left here, 8 for oxygen, 1 for hydrogen. We're going to start by drawing the oxygen. We know that we are working with an oxygen and 2 hydrogen atoms. So let's start with the oxygen. So in oxygen's nucleus, I'm just going to do an OX for oxygen. That's really small. I'm going to just move this up a little bit. And I'll turn this light on too. Okay. So we saw from the slide that oxygen has 8 protons in its nucleus. Neutral atoms, same thing we did previously. We have 8 electrons as well for an overall charge of 0. So let's do it. Let's draw the Bohr model for oxygen with 8 electrons. So 1, 2, 6 to go, right? Because there's 8 total, we've used 2. 1, 2, 3, 4, 5, and 6. And we ran out. We used all 8, right? So what we have here are two unpaired electrons. These are unpaired electrons. These two here. As you can see, the other electrons I drew in this second shell here are paired up. These two are unpaired, and they're going to play an important role very soon. Okay, let's draw the 2 hydrogens, right? So we have 2 hydrogens. I'll do that in green. And I'm going to draw them close by, starting with their nuclei, is plural for nucleus for the atoms. Just put an H in them for hydrogen. And let's do this one first, up here. Hydrogen has an atomic number of one proton in its nucleus. Neutral hydrogen has one electron. So we go to its first shell, we have one electron, and I just drew it like that. Same thing for the other hydrogen. Okay. Now, these hydrogens want full shells. This oxygen wants full shells, right? What's going to happen? Well, first, oxygen has how many electrons in its valence shell here? How many valence electrons in oxygen's outer shell? Not hydrogen. Yeah, 6. Has 6. Hydrogen has 1. Hydrogen has 1 electron in its valence shell. Oxygen wants how many? Wants 8. Hydrogen, how many does hydrogen want? 2, exactly. And this is what happens. I'll do it in blue. We form 2 covalent bonds, like that. So what's happening here is this pair of valence electrons is being shared between this hydrogen atom and this oxygen. And then the same thing here. This hydrogen is sharing its valence electron with oxygen's valence electron. So because of that, hydrogen now has 2. This electron over here is going to orbit around hydrogen sometimes. And then same thing here. Hydrogen's electrons really are going to orbit around oxygen sometimes. So that oxygen has 8 now, and then oxygen's 2 electrons will go ahead and orbit around hydrogen, so both of the hydrogens have 2. They are sharing electrons. These are 2 covalent bonds that form. So what happens, well, first I'll go over how we draw. We don't do this every time. As you can see, this takes a while to draw the Bohr models for all these atoms, but we draw lots of molecules a lot, and they're much larger. So what we do is a simplified drawing. So we call it the stick model. And so a water molecule in a simplified form looks like that. And we draw this solid line to represent a pair of shared electrons forming a covalent bond. Which equals a covalent bond. You might also sometimes see it kind of looking like this, where oxygen is kind of like this big circle like that, and then the hydrogens are attached to it like that. Okay, how are we doing on time? 3:47, doing great. Wow, we're doing really well. Perfect. Okay, any questions? Any questions about covalent bonds? Because I'm about to complicate things in a fun way. In a fun way. Because this isn't the whole story. Something else is going to happen. In fact, I might just leave this up and show you what's going to happen here. All right. Importantly, there's another layer of detail we have to master here before we can go on to our third bond, and it's called polarity. So if I ignore this. If we have time at the end, we can draw another. This is just drawing another molecule with covalent bonds, just like we just did. Good practice. So we might do this as a warm-up next time, actually, or at the end of class today. We'll get there. But okay, polarity and how water is a polar molecule is a very, very important concept. It actually confers many important properties to water. It's actually why when you mix water and oil, you'll never get them to mix together. Has to do with it being polar. But we're going to really focus on what polarity means, why it exists in water, as well as other polar molecules. And we're going to start by taking a look at our, we'll come back to this slide actually. But now that we drew water, I'm gonna write it up here in blue. Okay. Maybe I'll do purple because I did. No, I'll do blue. Blue is fine. Okay. First thing I want to say is that oxygen as an element has what we call a high electronegativity. So I'm going to write that in. This oxygen here has high electronegativity. All oxygen atoms do. Electronegativity. Fancy word, and we'll talk about what that means. Conversely, hydrogen atoms have low electronegativity. So both of these hydrogens here have a low electronegativity value. Okay, what does that mean? Electronegativity is a measure of an atom's tendency to attract electrons or pull them closer to that atom. So what that means is because oxygen has a high electronegativity, electrons love oxygen. Oxygen is this electron hog, okay? And electrons tend to spend more time circling and orbiting around the oxygen. On the other hand, hydrogens, because they have low electronegativity, electrons aren't really as into hydrogen. They don't want to spend as much time around hydrogen. So a majority of the time, electrons are attracted and spend more time around the oxygen. Okay. More electrons are close to the oxygen. So what this means is that in this bond where we share these valence electrons, in this one as well, these covalent bonds here, the electrons in the bond, because oxygen has high electronegativity compared to the hydrogen, the electrons in this bond spend more time around the hydrogen. The oxygen. The electrons spend more time around the oxygen in this bond, okay? So what we call this is an unequal sharing of electrons. So I'll write that as well. in both of these bonds, we have unequal sharing of electrons. It's kind of like if you have an older sibling. I'm a younger sibling, so this relates to me all too well. And the older sibling is kind of like oxygen, and you have a toy, and you know the parents try to intervene, but it doesn't work. And as soon as the parents leave, the big brother, big sister says, "No, I'm playing with it all day. I'm playing with the action figure or the Legos all day. Go away." And you only get to play with it like for 5 minutes, and they get it for like 6 hours. That's sort of what's going on here. Oxygen is this electron hog, and let's just say 80% of the time, the electrons in this sharing bond are around oxygen, and then 20% of the time they go hang out with hydrogen. It all has to do with this difference in electronegativity, and it's an unequal sharing of electrons in both of these bonds. And what we call this is polarity. There is a polarity in how these atoms are sharing electrons. And to be more specific about these covalent bonds, we actually call them polar covalent bonds. So these are, let me write, I wonder where I can write it. I know it's on the slide, but let's try writing it. I'm just gonna write it up here. These are polar covalent bonds. Okay, now, what does this implicate? What is gonna happen because of this? Because electrons, which are negatively charged, are hanging out around oxygen more, what charge is going to be given to that oxygen there? If electrons are spending more time around oxygen, more time negative charges are around oxygen, right? I kind of answered the question. But what this does is because more of the time negatively charged electrons are around oxygen, it gives it a partial negative charge. And to denote partial charges, there's this symbol called sigma. It's like if you're drawing the number 8 like that, but you don't finish it. So it looks like that. I'll do that near the oxygen. So you're drawing the 8, but then you don't finish it. And that's what sigma looks like. And then you put a negative. So because the electrons in these bonds are with oxygen more of the time, it gives oxygen this partial negative charge, which we symbol with, or use the symbol sigma as partial negative. This is a partial negative charge on the oxygen. Partial negative charge. It's not a complete charge, it's not completely negative, because the electrons aren't completely transferred, like we saw with the ionic bond. So if sigma, yeah, correct, sigma is what it's called. So if these negative electrons are being drawn closer to oxygen, the negatives are further away from hydrogen, what charge is going to be given to the hydrogens? Ryan got it. I like your name, Ryan, because it's my name. Partial positives, exactly. So we do a sigma positive here and here. And so what you'll notice about the water molecule, this is true for all water molecules, is that if I were to do, or if I were to cut this water molecule in half, let's do a dotted line through here. You'll notice that it has a partial positive end and a partial negative end. There's a charge difference across the water molecule, and this is what we refer to as polarity. So water is polar. Yes, so Addie asked if it's partial because it didn't completely transfer, and that's exactly right. Because the electrons spend maybe 80% of the time around oxygen, it's a partial negative. If it were to spend 100% of the time, then it gives it that full charge. It's a little complicated. I mean, we're talking about atoms, so the research into this was really difficult to sort of understand because you can't like film how charges move or electrons move around. But this is the general consensus that electrons are unequal. There's an unequal sharing. They spend sometimes around hydrogen, but most of the time they're around oxygen. Okay, so yes, you get this charge difference across the molecule, and it creates this polarity to the molecule. It's a polar situation. Okay. So that's what I mean by polarity. It happens when you have atoms of differing electronegativity that are covalently bonded together. It doesn't happen in ionic because ionic is full charge differences between the atoms. This is partial. Questions about polarity? I can go back to the slide as well. And here's the sigma symbol, by the way. The definition. So polarity is when you have a molecule with partial charge difference across the molecule, as you see here with positive and partial negative. Whenever there is a difference, yes, if there's a large enough difference in electronegativity, it gets kind of complicated, Grace, because you have to geometrically there has to be like a positive side and a negative side. Sometimes they kind of balance out, but for our purposes, if you have, and we'll talk about this a little bit more, but if you have a hydrogen or a carbon, something with low electronegativity bonded to an oxygen or a nitrogen, these are atoms with high electronegativity, you'll get a polar covalent bond and you'll see polarity there. I won't trick you and be like, no, it's not polar because of the arrangement. No. Chemists might. Chemistry class, you will. I always thought this sign was delta. Maybe it is delta. Is it not sigma? Maybe it is delta. I don't know the Greek. I always screw that up. I'm gonna Google it because I'm curious now, and we have time. We're making good time. So let me. Delta is a triangle, but it might also mean this. It sounds familiar. What is Greek symbol polarity? I'll be embarrassed if I'm wrong. Is he gonna tell me? Oh boy, it is delta. Oops. Okay. Delta. Hey, see, I'm human. Thank you. Okay, it's a delta, not a sigma. Sigma, maybe sigma is like wavelength or something. I can really screw those up. Is sigma like this? Looks like that or something? I don't know. No, wavelength is lambda. This is all physics, so it doesn't even matter, right? All right, so it's called delta. It looks like that. It indicates partial charge. All right, let's move on. Third type of bond, hydrogen bond. It's our last type of bond that we'll be talking about today. Actually, I'll leave that up while I erase. Okay, hydrogen bond. So far we've talked about the ionic bond, talked about covalent bonds now. That can be polar covalent bonds. If you have that electronegativity difference between atoms. If you don't, I'll quickly mention, if you don't have the electronegativity difference, like if you have oxygen gas, which is just O2, oxygen covalently bound to another oxygen atom, those are the same electronegativity, right? Because they're the same type of atom. And so they share the electrons equally, actually. And so we call that a nonpolar covalent bond. Just FYI. Okay. So let me see here. So hydrogen bonds, okay. Hydrogen bonds. Okay, importantly, hydrogen bonds are the weakest of the three types of bonds. And sort of talk about why that is soon enough. Do I have the next? No, I don't. Okay. Weakest of the three types of bonds. We represent it by dashed lines, so we'll take a look at that shortly. And I'll talk about why it's the weakest, because it's very important to understand why it's the weakest type of bond. Okay. So I'm going to go to the board and write the definition of a hydrogen bond. This is our hydrogen bond. So every word in this definition is very, very, very important as a detail. So a hydrogen bond forms between the partial positive of a hydrogen atom from one polar molecule and the partial negative of usually, I'll add usually, for this class it'll always be an oxygen or nitrogen atom from another polar molecule. From another polar molecule. All right, so like I said, we're gonna pick this apart because it's important to understand the difference here between hydrogen bonding and hydrogen bonds versus our previous two bonds. The main difference being that this bond takes place between different molecules. I'll say that again because it's a very common misconception. It was for me for a long time. So, you know, for many people learning biology. Hydrogen bonds occur between different molecules. They are never occurring, you're never going to see a hydrogen bond between atoms of the same molecule. We call those bonds intramolecular bonds. Ionic bonds, covalent bonds are intramolecular, but intermolecular bonds, like hydrogen bonds, occur between different molecules, bonds between different molecules entirely. So this is going to happen between the hydrogen atom of one polar molecule, so one molecule, and the partial negative of another, or of usually an oxygen and nitrogen, from another molecule, polar molecule. We're going to look at an example of what that looks like. That's actually why this is considered, or partly why this is considered a weak bond, because the atoms aren't so close within the same molecule, but there are these weak interactions between neighboring molecules. And we're going to take a look at an example of that in a minute. Okay, so it's between a partial positive of a hydrogen, always a hydrogen, that's why it's a hydrogen bond, of one polar molecule and the partial negative of an electronegative atom, such as oxygen or nitrogen. Those are the only two I want you to be familiar with that will form these kind of bonds, oxygen or nitrogen, on another polar molecule. So what's an example of molecules that'll form these types of bonds? Well, we just drew one, water. Water forms hydrogen bonds between different water molecules. Let's look at that. Let's take a look at what that looks like. Okay, and that'll be the last thing we do for the lecture today. Okay, so we just drew water. I'm going to draw the simplified form. H2O, right? So we've got water molecule. We just learned that a water molecule has polarity to it. So we draw delta symbols. A negative delta, partial negative on the oxygen, partial positive charges on the hydrogen atoms. I'm going to draw another water molecule, an entirely different water molecule right here. I'm going to make it sideways, like that. And this water molecule, also polar. All water molecules are polar. So oxygen with a partial negative, partial positives over here on the hydrogens. What do we know about opposites? They attract. And so we draw these hydrogen bonds as these dashed lines. And that's what our hydrogen bond looks like. So a hydrogen bond takes place between different molecules, always, never within the same molecule. These are covalent bonds, right? Polar covalent bonds. Different molecules, and they're always two polar molecules because it occurs between a partial positive on a hydrogen and a partial negative on an oxygen, or if it's a molecule with nitrogen in it and it's a partial negative nitrogen, can happen there as well. Okay. In the last minute, I'll just show you this funny way to remember this sort of thing. Like this. What does that mean? So if this is your water molecule, and here's your oxygen, and these are the two hydrogens, then it's going to bind to other, or be attracted to other water molecules, form hydrogen bonds with other water molecules, like that. The hydrogen attracts to that partial negative on the oxygen, the partial positive here, partial negative on the oxygen, and then you can have another one there, and there, and there, and so on. But yeah, that's it for today. Any questions about today lecture? Finished all three of our bonds, and next time we're going to talk about water and the properties, more about water and its properties, largely to do with these bonds that it can form. Okay, no questions. It's 4:15. Oh, so the negatives attract the positive. Yeah, exactly. So the partial negative charges, or a partial negative on an oxygen here, will be attracted, on this water molecule, will be attracted to the partial positive of the hydrogen atom on this molecule, and it'll form this hydrogen bond. Intermolecular, between more than one molecule. Okay, so let's take 5 minutes, 5-minute break before the lab mini lecture. And like I said, during this mini lecture, I'm going to go over the journal assignments a little bit, a couple things about it, and then we'll do the lab lecture. 5 minutes? Or do people want 10? 5 or 10? Type in your vote. Yeah, 10 sounds pretty good to me too. Can go to the bathroom. Yeah, let's do 10. I agree. Yeah, it's too much. All right, let's do 10 minutes. So let's meet back here at 4:26-ish, 4:26, and we'll talk about no break. I need a break. We usually take a break between lecture and lab. So let's do 10 minutes, and then we'll talk. I'll get the music playing. That's a good one. So I'll see you soon, 4:26. It's a little bit funny, this feeling inside. I'm not one of those who can